let's go on with the pipe dimensions. See, for a laminar flow, for the velocity profile to develop, we need some particular length that is called hydrodynamic entrance length. I will show you how to calculate it. I have taken the diameter of my pipe as 1 centimeters, and since it is laminar flow, the maximum value of Reynolds number can be 2000. So for laminar flow, the development length is given by 0.05 into Reynolds number into diameter. Based on this, I have calculated it over here, 0.05 into E13, that is Reynolds number, into diameter, that is diameters in meters, that is 0.01 meters. This is how I calculate the length of the pipe. Let's go with the geometry creation. Fine. Now I am in the user interface of Ansys ICEM-CFD. Geometry. Our pipe is a cylindrical object. That is, for a simple cylindrical object, we can create the geometry in Ansys ICEM-CFD itself. If the geometry is a little bit complex, we can go for other modeling tools and import the file as an IGS file over here. Okay, let's get started with geometry creation. Create point. Explicit coordinates. The first point, let it be at 0, 0, 0. Apply. First point is visible now. The second point, I have said that the length of the cylinder is 1 meter. So second point is 1 meter along the x-axis. Click apply. Done. Now the second point is also created. Now we will go on to the surface creation. Create a modified surface, and it is simple shape. So we will click standard shapes, and under that we will click cylinder. My cylinder diameter is 1 centimeter, that is 0.01 meters. So it will be 0.005 meter radius. Both at point 1 and point 2, my radius is 0.005, 0.005. Now I will click the two axis point, that is this one, done. Now I have created the cylinder. You can just check it out like this. For rotating the cylinder, click the left mouse button and drag it. You can rotate the geometry. The second point is blocking. Before blocking, let us name the parts. The boundaries, that is inlet, outlet and the wall. So under the part, right click on part, create part. Now inlet. Okay, I'll just click select entities. This will be my inlet. Inlet is a surface. I have wrongly clicked the edge. So what we will do to cancel it, I will click right click. That's it. It will get cancelled. To just click surfaces, in the select geometry tab, see, I will remove curve selection, body selection. I will just enable only the selection of surfaces. Now if I click over here, only the surface is selected. If I click the middle mouse button, inlet part is created. Now what you will do is I will create an outlet. I'll just type outlet over there, then come over here. My only surface selection is enabled. I'll click it, middle mouse button, outlet is created. Now what I will do is I'll create wall, done. Now I have created inlet, outlet and wall. Now to create the body, that is, we have just created the surface. To create the body, what we will do is we will click on create body. Okay, and since our body is a fluid domain, we will type vFluid. Okay, we have done it. Now to specify the body, that is, the body is like inside the cylinder. To specify it, I will specify centroid of 2 points, that is this point and this point. Anyways, the body will be in between it only. So I will click screen location, 1, 2, middle mouse button, done. Now the body is also created. Now this part is done. let us go. What is the next step? Blocking. To blocking, just go to the blocking tab. In that, create block option is there. Click it and just click 3D bounding, the 3D bounding box. Since this is the only thing, you can either click select geometry and drag to select the entire surface, or else if you click apply itself, the block will be created. The block is nothing but a box which completely encloses the cylinder. If it is some other shape also, there it will be a box which will completely enclose that geometry. The next step is associate the block to the geometry. If you see here, associate block to the geometry. To associate block to the geometry, just click under the blocking tab itself, click associate. What we will do is associate edge to curve. So what you have to know some details over here. An edge. What is an edge? Both the block and the geometry, that is our fluid domain, both are simple geometries, but we have given some nomenclature differences. That is, for a block, an edge or a curve is only called as an edge. For geometry, an edge or a curve is called as curve only. So we are clicking associate edge to curve. Here click Hexahedge means we should click the edges of the block. Fine. Now see, I have some discomfort over here to click the edges of the block. So what I have to do is I have to rotate. That is, if you are in some command, you cannot simply click the left mouse button and drag it to rotate the component. So what I will do is I will just toggle dynamics. Under the select blocking edge, I will click toggle dynamics. So it has come out of the command, but it is actually live. If you click again, it will go into the command. So I will click that, it will come out of the command. I will drag and rotate it so that I have come over here, most suitable position, so that okay, this is a very better position. Now you see, select Hexahedge. Hexahedge means what we want to do is, like, these 4 edges should be associated to this circular curve. So what I will do is now select Hexahedge only, right? We will click on the edges. 1, 2, 3, 4. We will click middle mouse button. Now comp curve, that is, this is the curve of the geometry. This circular curve I will click. Done. Now I have to do the same thing for there. So hope we are comfortable with how to rotate and toggle and those things. Okay, this is a comfortable position for me. Okay, select Hexahedge. 1, 2, 3, 4, and I click middle mouse button. Now computational curve, that is this thing. Done. Now I have associated the edges of the block to the curves of the geometry. Okay, I have done. Snap project vertices, that is, these are the vertices of the block, that is the points, the corners of the block. What it is right now outside the geometry. So what we have to do is we have to make it come inside the circle. To make things clear, I will uncheck few items in the geometry, that is curves. Let surfaces be there. Okay, let curves be there, the surfaces may not be there. Now I'll click snap project vertices. It is already in all visible. If I click apply, okay. Now if you see here, the block has come inside. With this block, we cannot define the mesh parameters effectively. For that, there is a thing called split block. Under that, there is an option called O-grid block. Okay. Now, to create a O-grid block, you just have to select the end faces. So if you click select faces. These are the faces. One. We have to go to the other end. Now come again. Click this face. Done. Now we have selected the faces. If I click apply, the O grid block has been created. That is, you see, you can understand and appreciate what is O grid now. See, initially there were no such thing running diagonally, and there was not a square block inside. Only one complete outside block was there. It was not enough to define the mesh parameters accurately. If you have a diagonal thing, you can define the mesh fineness near the walls and those sort of things. Okay, now let's get on with the mesh parameters definition. Okay, pre-mesh parameters. Now I will click on edge parameters. I will click the select edges. Let me first select this edge. Okay, and I will make sure that copy parameters are checked and method to all parallel edges are checked. What I will do is I will give some number of nodes, 15. Let the number of nodes be 15. I don't want any ratio, that is any geometric ratio how the nodes grow from here. So what I will do is I will click the ratio 1 as 1 as well as ratio 2 as 1. You need not worry about the spacing 1 into 10 e to the 1 power 10 like that. The spacing is actually 0.0005. This is the actual values that is available in the geometry right now. Okay, fine. Ratio 1, ratio 2. I will come to ratio 1, ratio 2, those sort of things while defining the mesh fineness near the wall. Okay. If I click apply, done. Now I will select this edge. Let me give 15. I again don't want any geometric progression ratio how the nodes should be spaced. If I click apply, then what I will do is I will click this edge. This is how we have to define the mesh fineness. If I click over here, and we cannot randomly, if I give some 11, let me give 11 nodes. Now the spacing and the ratios over here are important. That is the spacing, the height of the first cell is important. So what you will do is to calculate the height of first cell, I will again go back to the Excel file. So if you see over here, for Reynolds number less than or equal to 2000 laminar flow, the first cell height is pipe radius by 38, that is R by 38, which will be diameter by 76. If I do that 0.01 by 76, which will be 0.00013 meters. So I have to specify this value somewhere. So this is done because the first cell height, or for turbulent cases it is the y plus value through which you will calculate the first cell height. These values are important because the flow dynamics near the wall is the most important. If you have to capture the physics near that region, you have to define the mesh very fine meshes in that region, that to a precise calculated value. So in our case it is 0.00013. So I will try and specify this. Now the spacing one, the arrow starts from this point and ends at this point. The spacing one determines the space of the first cell, that is from the wall to the next node. That is the first node starts here, the second node is somewhere here. So this is the distance between the two starting nodes is called spacing one. That I will give 0.00013. 0.00013. And this ratio 1 which I have given as 2 is like how the spacing grows. that is it grows in the ratio of 2. That is, if the first spacing is 0.0013, the second spacing is will be twice that of that. The third spacing is 2 to 4 times of that, like that. It goes on in geometric progression. That 2 is a very crude value, so what I'll do is I'll give 1.3. Then spacing 2, since the edge ends here, that is the line here, if you see the arrow, it ends here. Since it ends here, the spacing 2 is like the length over here, the space, the region, the distance between the last and the last before node. So spacing 2, it need not be very fine. So what I will do is, I will not specify anything, let it set itself automatically. Okay. Fine. Now if I see my ratio 1, it is 1 over here. So I don't want that value. So what I will do is, with this spacing and to achieve this 1.3, the actual value is 1, but my given value is 1.3. So what I will do is, I will increase the number of nodes. To do that, I will just click here. If you see, both the spacing 1, the actual value and the given value are matched, and the ratio is also matching now. The spacing 2 and those things, it will take care of itself. Now what I will do is, I will click apply, and I have defined the mesh within this space. So linear wise, I have to select one edge and give the how it is spaced linearly. If I click it over here, click it, and what I will do is, I will give some, it is, since it is 1 meters, even if I give 500 along the length, the mesh need not be like vary from the wall or those sort of things. It may be uniform. If I click apply, to visualize the mesh, we will go into the blocking tree, that is in the model tree under blocking, we will click on pre-mesh. So it asks the mesh to recompute. Okay, the mesh has been created. To visualize it, we will click the solid thing, and to remove these things under the geometry, we will remove the edges. Okay, if we go and see, yeah, okay, if we go and see the meshes, the region near the walls is small and it grows outward. That is, it starts from a small value and slowly increases to a larger value. And at the center, it is very fairly simple value. Now let us go to the side view. Yeah, this is actually front view. If you see the mesh, how the mesh is uniform, as I said, there is no fineness near the walls and so on along the longitudinal mesh. So the mesh is pretty uniform. But the thing is, this mesh is little bit coarser along the longitudinal direction. We may go on and change it. Just click the edge again and you increase the number of nodes. It will take care. Now what we have done is, we have created the mesh, pre-mesh actually. To export it, the next step is export the mesh file. To export the mesh file, we have to do the following things. Right click on the pre-mesh, click convert to unstructured mesh. Yeah, you need not worry about anything. That is now under the model tree, a mesh tab has been created. You need not worry about anything. This is just a procedure. Unstructured doesn't mean unstructured mesh. Whatever you are defined as a structured mesh, it has only hexahedral cells throughout. So your mesh will be an hexahedral mesh only, hexahedral structured mesh only. You need not worry about it. What I have done is like a procedure kind of thing. Now go to output mesh. First thing is output mesh tab. First thing is I have to select the solver. It is always better to give the solver as Ansys Fluent. This if we create a mesh file for Ansys Fluent, that can be used for OpenFOAM, star CCM and so on. I click apply. Okay, I have selected the solver. Now go to write input. Just click yes, whatever dialog box is open, just click those things until you come over here. Now our mesh is 3D. For write binary file, give no. We have to get a ASCII file only, so you should be giving no. Ignore couplings, no. Then the name of the output file is that you have to give over here. Here it is C uses Vijay Fluent. You have to change it to some other else. Let it be pipe flow.ml. Just type pipe flow. If you click done, yeah, your pipe C users Vijay, yeah, pipeflow.msh mesh has been created. That's it, your mesh file has been created. Thanks for staying through the video. It is a 61 MB file. Thanks.